In this video, we're going to go over this question where you're given a graph of an updating function and a diagonal, and you're told to consider the following statements. And so what we're going to do is we're going to use the cobwebbing method to figure out if these equilibriums are stable or not, and if the solutions are increasing or decreasing. So in statement 1, it says that the non-zero equilibrium is stable. What is the non-zero equilibrium? The non-zero equilibrium would just be this point right here, which is going to be 1. And the zero equilibrium is just over here. So we have two equilibrium points. And so to figure out if the non-zero equilibrium is going to be stable or not, we have to choose two specific starting points from both the left and from the right of that non-zero equilibrium. So we could start from, 0.5 and see what happens. So when you do cobwebbing, we see that the red function is the diagonal. It's just y equals x, and then your blue function is the actual updating one. And so for cobwebbing, what you want to do is you want to start at your initial value, and you want to go up to the updating function. And once you go here, you want to let the cobweb lead the way. Don't overthink it, just let it lead you. So you went to the top, to the updating function. Now, which way do you have to turn to go to the next function, which is the red? You can go this way, obviously. The only way to go is this way. Then you keep going up, right, up, right, and so on. And as we see, it is increasing. We're moving towards the non-zero equilibrium. So we know what the behavior is from the left. What about from the right? Why don't we choose something like 1.5? So we're going to go all the way up to the updating function, which is the one in blue. And then what do you do from here? How are you going to go to the red function? So the way we're going to do that is just by going left. And then you just have to go down to the updating, left to the diagonal, down, left, down, and so on. As you can see, we are moving closer to the non-zero equilibrium as well. From both sides, we are moving closer, and so therefore it is stable. Now, what about statement 2? Well, we pretty much just already did this. We saw that when you start at 0.5, the solutions actually end up increasing towards the top. So yes, this is true as well. And then what about here, where it says m star equals 0 is an unstable equilibrium? Well, we're going to have to see what happens when you choose a starting point from the right of 0 and from the left of 0. Here we see we already chose one to the right of 0, which was 0.5, so we don't need to bother for that again. We see that it's actually moving away from the zero equilibrium over here. So right now, we know that this is half stable. Now we need to figure out what happens when you do it from the left as well. So, I don't know, let's do like negative 0.5 right here. Or actually, let's go a bit closer here. And so right here, I guess this would be like negative 0.25. So you would go to the updating function, and then you'd have to turn left, and then you keep going and going and going. And as you can see, you're moving away from the zero equilibrium here. And so therefore, because you were moving away from the zero equilibrium from both sides, that means that this is indeed an unstable equilibrium. So this is definitely true. And then for part 4, it says the solution starting at m naught equals 1.25 is decreasing. So we did 1.5. Even if you started at 1.25, it's going to be the same thing, because you'd be starting here, going to the updating function, and then you have to turn left, down, left, and then so on and so forth. You'd be increasing. Sorry, not increasing, you'd be decreasing, but you'd be moving closer to the equilibrium. And because it is decreasing either way, that means that this statement is definitely true. So we can say that these are all going to be 1s.